Okay, last topic in chapter 2 is directional derivatives. So we've talked about partial derivatives and how you put them together and make a gradient, and we can do all sorts of cool things with that gradient. But partial derivatives have a bit of a limitation that directional derivatives will solve. So let's go ahead and talk about that. So partial derivatives, you can only move, let's think about this on the xy plane. When I'm taking a partial with respect to x at some point, let's say 1, 2, I can only move in the x direction. I'm restricted in the y direction, so I can only make movements in the x directions. On the other hand, if I do a partial with respect to y, let's say at another point, just to make more space on the graph, let's say at the point 2, -4, at this point, and again, there's some surface that lives over top of this, but we're just focusing on what's happening in the xy plane. If I take a partial with respect to y, y is the thing that's varying, x is held constant at 2, and so I'm allowed to vary in my y direction. X equals 2 restricts me here. I can't move off of this x equals 2 line, but I can move in the y direction a little bit from there. And I can only make small changes as well. I mean, that's something we've emphasized, that when you're on a surface, at a point on that surface, your tangent plane is a local approximation, right? My surface doesn't look like this plane. It only looks like that plane locally. I could also imagine this surface as made up of a bunch of tiny little tangent planes that are all stitched or quilted together. And there's actually like the Epcot Center looks like a bunch of little planes to make the sphere of the surface. And so tangent planes are local approximations. The further you move from your point of tangency, the worse that approximation will get for most surfaces. And so again, these only give you restrictions in the type of movements that you can make. Or if we think back to our, we had a bakery, remember we had a bakery, and z was a function of x and y, and we were making cookies and donuts. And then we had money that was coming in. We could only say, what happens if I make one more cookie or one more donut? But what if you wanted to make a change that involved both? You want to say, I want to make a little change in, maybe I want to make one more cookie and one more donut, what happens? We couldn't answer those questions with a partial derivative because we were restricted, right, in these ways. So another way of thinking about that type of question where I want to change both, maybe what I was here, in our bakery example, we'll do that red, there was at the point 1 cookie, 1 donut, and I wanted to change both of them. I wanted to know if I made a movement in that direction, 1 more cookie and 1 more donut, what happens to z? What happens on the surface where I'm making movements that aren't perpendicular, that aren't like the moving like the y-axis or the x-axis, but maybe I'm moving at an angle, tilted. So I'm not perpendicular, I'm at any other angle. Okay, and those are achieved through a directional derivative. They give us a lot more freedom and flexibility. And it turns out directional derivatives are related to partial derivatives. In fact, they're just a weighted average of your partials. And we have to get used to some notation. They look kind of funny. We're going to say that a D, maybe I'll be consistent with what I have in the book. I think I did. Instead of A's and B's, X naughts, Y naughts. We have to have a couple more caveats because we have to say a directional derivative in a particular direction, because now we don't know. When we say partial with respect to x, we knew only x was varying and it was perpendicular to the x and perpendicular to the y. So we have to say in the direction of the unit vector u. What's a unit vector? Vector of length 1. So if they give you any other vector, they might give you a vector v that's not of length 1. You can force it to be a unit vector by normalizing it. Back to chapter 1 ideas. We'll practice one of those. So we're going to take a directional derivative, and that's going to be this capital D thing, in the direction of the unit vector u. And u is going to be given by these components A and B. And we'll do it at the point x naught, y naught. So that's our point of tangency. Right. We'll do it at the point x naught, y naught for our function in the direction of u, which is a unit vector. And this is the formula. And it turns out it's just a weighted average of your partials. It's a times f of x at the point x naught, y naught, plus b, that's a y, x naught, y naught. And there's a shorthand way of writing that too, because if you take your partials and put them in a vector, you have a gradient. So we could say this is really the gradient of f at the point x naught, y naught, dotted with the unit vector u. So again, the first line kind of shows you this weighted average, that it's some weight A times your partial with respect to x, time plus some weight B, this weighted average idea, of your partial with respect to y. And then a shorthand way of saying that is just dotting, dot product of the partial with respect to, or the gradient with your unit vector. Okay, so let's look at an example. Let's do this problem. Find d of u. Let's just write it this way, write it all out. Find the directional derivative for f of xy is x squared plus 2y squared in the direction minus 2, 1 at the point 3, 2. All right, so let's see what's happening here. Let's think visually. Always a good way to start all the problems. Some of these surfaces you, again, should have on top of your head. Otherwise, get your tech tool, get your favorite calculator, get your TI Inspire, get CalPlot 3D. Let's see what the surface looks like. Go to the point on the surface, and then let's think about this direction. So first thing, directional derivatives have to be, the definition has to be a unit vector, which means length 1. Ours is not. Right? This is not a length 1 vector. You should be able to see that right away. Otherwise, let's get the length and show that it's not a length 1. So let's call this vector v. How do you get the length? Denoted with these bars. It's the square root of the component squared. So minus 2 squared plus 1 squared. So it's the square root of 5. Definitely not 1, so not a unit vector. So I can just shorten this. So at the point 3, 2, we're going minus 2 up 1. So that's b. And it's too long. So how do you shorten it? Well, to create u, the unit vector, you just take v divided by its length, right? That was, again, something from chapter 1. And it's going to point in the exact same direction. It'll just be the right length for us. It'll look like that. Let's go ahead and compute it. So it's going to be minus 2, 1 divided by the square root of 5, which is just minus 2 square root of 5, 1 square root of 5. So that's like 2 over 2 point something, so like minus 1 in the x, about 1/2 in the y. Yeah, so it's this vector here. This longer one is v, the shorter one is u. How do you know that's length 1? It is by design, but you could check. Go ahead and get the length of u just to check. The square root of the sum of the component squared. So minus 2 over square root of 5 squared plus 1 over square root of 5 squared, square root of 4/5 plus 1/5 is 1. Okay, so we did a little bit of prep work to make this actually fit the definition of directional derivative. We can only do a directional. Say they're saying on some surface, this surface, walk in the direction of v. But don't go all the way in the direction of v, because we can, when we do derivatives, we can only do small changes in x and y, x or x and y with a directional derivative, but they have to be small changes. And again, they have to be small changes because that tangent plane that we're on, or the tangent line that we're walking along, any of those things of tangency are only good locally. That's why we force this to be a unit vector. That's why we only say 1 unit change in x or 1 unit change in y when we do f sub x and x sub y. Okay, so we did a little prep work. Now we're ready to apply this new formula that we have for the directional derivative. But let's do a little more visualization. What does the surface look like? So there's actually some surface over this xy plane. Well, is this a familiar one? If it didn't have the 2 there, it's our circular paraboloid opening up from the origin. So this now makes an elliptic paraboloid, so it's just gotten squished some way. So we have what's coming out from the board, an elliptic paraboloid, and we want to know how much when I walk in this direction from some point on that surface, so elliptic paraboloid here, at some point, and I walk in that direction, in the direction v, which is the same as in the direction of u, but I only go u in length along that, what happens to the z value? Does it go up or down? Again, if you did a good visualization, either in your desktop coordinate system, in your corner coordinate system, or with a tech tool, you maybe could take a guess as to whether that's going to be positive or negative. But if you just go straight away with the algebra and the calculus, you don't even need to make a guess and just let the calculus follow, and then you can check your work at the end with the tech tool. Okay, so now we have our values for the a and b. So this is your a, this is your b. Last piece of the puzzle we need is to get our partials. So f sub x for any xy, easy one. 2x, f sub y for any xy, another easy one. 4y. Evaluate that at the point of tangency, which is 3, 2. So f sub x at 3, 2 is 6. F sub y at 3, 2 is 8. So now I'm going to take these things and do them in this weighted average. So my directional derivative, how much I change when I walk in the direction u along my surface, which is this elliptic paraboloid from the point of tangency 3, 2, is going to be a times f sub x at 3, 2, plus b times f sub y at 3, 2. And we have all of our components. So fill in our a, fill in our partial, fill in our b, fill in our partial. A was how much I move in the x direction. B is how much I move in the y direction. This is about 1, so I'm going about 1 in the x. And then I'm going about 1/2 in the y to get to that u point. Then my f sub x at 3, 2 was 6. My f sub y was 8. A little bit of arithmetic. We'll have what? Minus 12 plus 8 is minus 4 over square root of 5. What is that? About, looks like maybe about 1, right? All right, no, about 2, about minus 2, roughly about minus 2. So we're going to go down in z units about 2. So if we were doing our bakery example again, z was a function of x and y, cookies and donuts. Not possible to do this, but if it were, well, I guess you could cook a smaller cookie. We're saying now we want to make this fraction -2 over square root of 5 is about a -1, so make about 1 less cookie, make about 1 more, that's about roughly one more donut. What happens to your z value? Well, it's going to go down because we made less cookies in that scenario. Okay, let me show you a few tech tool things before we finish up this content. So Calculate 3D again has some really cool features. Okay, so our surface was a little simpler this time, x squared plus 2y squared. Yeah, there's our elliptic paraboloid. I should use the arrows here, a little bit easier to see. Yeah. See how it is elliptical, it's kind of squashed. The tangent plane is showing there, and we know again that the tangent plane when we get to 0 should be horizontal. pretty close to 0 right now, but you can enter values there. But what I wanted to show you this time was about your derivatives. So click this little arrow next to the 2D plane here. Hide all objects for now. Again, we're in this XY plane over here, and there's things we can show. So we've shown the tangent planes, we've shown the gradients. You can input a point rather than following that little blue dot. We'll get to normal vectors later. Okay, the trace of a tangent line, and then we're going to do the directional derivatives as well. There we go. Okay, so these are, you can see on the graph as I slide this blue point, these are the traces of f sub x. So these will be when we're restricted to be in the y equals, whatever, y equals 1.3 plane here at this point. And this is the intersection of the y equals 1.3 plane with the surface, and it makes this parabola. So it's a slice through it. And then it'll show you, let me zoom out. There's the blue point. It's hard to see. Maybe rotate. Oh yeah, there's our blue point up there. And the tangent line, harder to see, is this black line here. Maybe making the surface transparent could help. So making the surface a little more transparent so we can see through it. And from the top. There we go. Then you can see a little bit better that way. That black line is the tangent line. This is the f sub x. In this blue, and so in this green bar up here, this is your f sub x at that particular point. Has this value. The slope of the tangent line in this case is 2.8, positive 2.8. So that's a way it's visualizing that we did with that activity with the hemisphere. And this is another way you can visualize it. And it also shows the calculations there. You can do, that was our f sub x, you could do the f sub y traces over here, or you can do your directional derivatives. So directional derivatives, this is a 45-degree angle, but I think what we'd rather do is enter the direction vector. So we were looking at a vector, let's see, what was that? -2 divided by sqrt of 5 for square root, and positive 1 divided by sqrt. And so at your particular point, it's going to show oh yeah, there's our trace. Oh, that's pretty cool. The trace along the curve. These are as your direction vectors moving about, whatever point you're on. And you'll see your directional derivative. I need to hide all objects, get rid of some of these. Yeah, so there at the top, there's our notation. In the direction u, which is you're controlling down here with this, you'll see in the direction 0.7, 0.7, that's your u. This is how much the z value is changing. And you can also ask computational tools like Wolfram or Simolab to do directional derivatives as well. Okay, so that is the end of chapter 2 of journal 3. So learned a lot in that one, right? So let's just go over the topics real quick. Partial derivatives with respect to x, with respect to y, partial derivatives of higher dimensional functions, second partials, marginal interpretation of the partial, geometric and visual interpretation of the partial, how is slope of a particular tangent line restricted in a plane, tangency, how to get a critical point, how to get a tangent plane, and directional derivatives. So lots of topics there. And then you're now ready for challenge prompts at the end of this chapter. You have your choice of 3 or 4.